All right. How's it going? So, questions? Yeah.
The Control D, it basically just prints into file. Whatever you do.
So if you're doing a get car and you hit Control D, it causes get car to return a -1, which in standard IO.H is set up to be what EOF is equal to.
Just check if like the car is equal to EOF.
Yeah, check if the car is equal to uppercase EOF. Yeah. Yeah, and it's really just kind of a convention. Right, so we'll just call get car, we'll put in its return value. So if I type in uppercase A, it tells me get car return 65, followed by 10 because I hit a new line. Right, I hit the enter key. If I do ABC, it returns 65, 66, 67, and then a new line. If I hit ABC, followed by a Control D, it returns 65, 66, 67. So Control D, if it's not the first character on a line, says go ahead and take everything I've typed so far, send that to standard in. And then get car picks it up on the next 3 times through the loop. But if you hit Control D in the beginning, get car returns -1. But that's all that Control D does. It's not actually the end of anything, right? Because I can go back and I can say ABC, and it picks up those characters. And I can say hello. Right, and I can hit Control D a bunch of times and it's -1. So the understanding is that when you get to the end of a file or when you hit Control D, get car will return -1, and they'll expect you to do something with that. And if I redirect standard in, say from a file, right, this is all the stuff that it read from this file EOF.c, and when it hit the end of the file, it gets a -1 every time it tries to call get car. But since my code's not responding to that, it just keeps reading -1. So it's another one of these conventions, right?
Can I see the code again?
Yeah. All right, other questions?
Can we talk about how to sell out a pointer to a list of doubles? So like a pointer to a pointer or integer.
Can I ask why?
So that you can index it as we index with phrases that you're using?
Okay.
Or is there an easier way to do that?
So first of all, do you need doubles or do you need ints?
Ints.
Ints, okay, so we can do ints. And how many ints do we need?
However many ints you have strings that you're taking in, phrases that you're taking in.
Okay, what's the maximum number of phrases?
It's just however many you take in, right?
Except it says you only have to remember 1,000 phrases.
Okay.
So you can do something like integer phrase count bracket 1,000. It's really all it takes.
Is there another convention for later on?
Mhm.
If anything comes up, would there be a convention for that?
For what?
Setting up a pointer to a list of memory locations that you're going to store your
If you really mean what you just said, a pointer to a list of memory locations, right? That would be something like int star locations, however many you want, right? So now this is an array of 1,000 integer pointers, right? And if I wanted to access a particular integer, I could say locations bracket 5, and I could say star, and that would be the thing pointed to by the 5th entry in that array of pointers.
So a pointer to the, oh, never mind.
Okay. We'll do this till we're blue in the faces on 222. So we'll definitely be getting there. But I think everything we're doing in this course, we can really avoid dealing with pointers for the most part. We have to use ampersands when you do scanf. We have to use, int star in a function if we're passing an array and we don't know the length of the array, right? But in our function, we can just say var bracket whatever, right? So we're using pointers and we're using addresses, but we can really just kind of think of them as arrays with peculiar syntax we need to keep the compiler happy. For this course, 222 will actually deal with this and this and break down exactly what's going on with that. And we'll spend a lot of time in GDB looking at memory and sort of getting really comfortable with these. And that'll be necessary because 222 is basically all about organizing memory to do things for you, right? Taking pieces of information and arranging them in memory in very particular ways so that we can pass them around and manipulate them. So we'll definitely get into that stuff. All right. Let's see if I have a network. Yes. So here's some ODP 419 code, right? And we sort of broke this down yesterday. But say val is a global variable, right? So it's declared outside of any functions. So every function below that has access to that variable, unless you declare that variable to be local. So put takes an argument I, and it basically sets say val equal to I, and then get returns the value of say val. So when you call put, whatever value you put in the argument gets stored right here, and when you call get, it just returns whatever value is stored. So that's your basic put get routine. If I called this variable say val instead of I, right, say val is now local to this put function. So when I use say val, I'm not referring to this variable up here. If I say integer say val, I'm referring to a local variable, which is the argument. So don't call a variable say val unless you want it to be local from this point on. Right, if you want the global, just access it. And I lost the network. So ODP 420 is basically the same thing, except your put function takes two arguments. It takes the location where you want to store a value, and then the value you want to store. And get takes the location that you want to get a value from. So outside of your functions, instead of saying integer say val, just make it an array. And the instructions say that this argument goes from 0 through 9, right? So you need to be able to save a total of 10 values. So if you make an array that holds 10 things, right, the rest of your code is more or less the same. Your put function takes an index and a value, and it saves that value at that index in your say val array. right? And then get just reads from that element and say val. So it's really a pretty small modification to 419. So code that up and test it. And sample code, right? Don't just make it so it can do these 4 put instructions, but sample code, if you put 100 at location 2 and 14 at location 1, and then you say get location 1, it should return a 14. If you get location 2, it should return a 100, and so on. And then test bed and /temp, go ahead and compile it up and assess it. So any questions on those? Okay. All right, PA4 questions. Super duper get card. All right, so I was supposed to talk about sorting yesterday, and I forgot to do that, so we'll talk about sorting today. Because when you run PA4, right, you build your index of phrases, and at the end you need to print out a list of phrases that's been sorted by length. So, I'm done with the server. So here's my War and Peace test file. And if you take the output and look at it screen by screen, the phrases are in increasing length, right? I don't care what the order is. If you've got 3 phrases that are all the same length, you can do them in any order that you want. But the 2 character phrases come, and then the 3, and so on and so forth. So you want to sort your output like that. So let's talk about sorting. So there's a set of numbers, and you want to sort these. You want to arrange them from smallest to largest. So you, as a human, how would you do this?
I'm finding the smallest number first.
Okay, so let's find the smallest number. That's a 1. Let's put that in our output.
Well, 0 is the smallest.
Oh, 0 is the smallest. Okay, so we'll put that in our output. And then find the smallest, ignoring that number that you just found. So that looks like a 1. Put that in your output. So I'm underlining these so I ignore them. And now find the smallest number that's not underlined. That's a 2. So underline that. And keep going. Right? That's a great way to sort things. And that's actually something called a selection sort. Because we go through here and we select the first element we want to put in our output, which is the smallest. And that goes in the output. And then we go through and we select the next element we want to put in our output, and so on. Okay, we'll go through all of these in gory detail in 222. Okay, plus a whole bunch of other sorts. But that's a first order sort algorithm, is a selection sort. A different way to sort is to simply begin with the first number and say, okay, where should this go in our output? Well, it's a 2, it's the only number in our output, so I'll just put it right there. Then move on to the second number, which is 10, and say, where does that go in our output? Well, it has to go after 2, so I'll just put it over here. And then go to your third number, 5, where does that go? Well, it's got to go after 2, it's got to go before 10, so I'll put it in here. And then go to your next number, there's a 3, well, it's got to go after 2, but before 5, so I'll put it in here. And basically, we go through our numbers in order, but we place them into the relative proper position in our output. Okay, this is called an insertion sort. Selection sort, the sorting happens when we choose which number we're working with. Insertion sort, the sorting happens when we put the next number into our output. Okay, and these are both reasonable sort methods. But the kind of classic go-to is a bubble sort. So I think you do bubble sorts in 121. And bubble sorts are not very efficient, but if you're only dealing with a few thousand, a few 100,000 phrases, bubble sort's plenty fast. So the idea of bubble sort is we make a series of what we call passes through our data. And if you think of these data as being rocks of different sizes, where the 10 is a very heavy rock and the 0 is a tiny little piece of sand, right? This isn't really how rocks and water work, but run with it anyway, right? The heavy rocks will tend to sink to the bottom and the lighter rocks will tend to rise up to the top, right? So we would like this 10, which is the heaviest of all the numbers, to sink all the way down to the bottom of this pile. And we'd like
just crush like pebbles of like different metals and water.
Yeah. So we'd like the 0, which is the lightest, to bubble up to the top. Okay, even though everything sinks. So we make a series of passes, and each pass through our data, the goal is to get one more number into the correct position. Right? In particular, to get one more of the heaviest numbers down at the bottom into the correct position. So our first pass through this data, we'd like the 10 to end up down here. And the second pass, we'd like the 8 to end up in the second spot. And the next pass, we'd like the 7 to end up here, and so on. And after we do enough passes, all of our numbers will be in the correct position. So what does a pass look like? Instead of going through and saying, what's the biggest number out of all of these, we compare each number to the number after it. Okay, so we start at the beginning and we compare the 2 and the 10. And we'd like the larger of those numbers to come second and the smaller to come first. So we say, is 2 bigger than or less than 10? Well, 2 is less than 10, so these are in the correct position. Okay, so I'm going to leave the 2 where it is. What about the 10 and the 5? Right, 10 is bigger than 5, those are in the wrong order, so I'm going to swap them. So I'm going to put a 5 here, and I'm going to put the 10 here. And then I compare this third number, which is now 10, to 3, and those are in the wrong order, so I'm going to swap those. So I'm going to put a 3 here, and a 10 down here. And then I compare 10 to 1, and those are in the wrong order, so I swap them. And you can see what's happening. This 10 is falling down to the bottom of the list. 10 versus 8 is in the wrong order, so that's an 8 and a 10. 10 and 7 will swap. 10 and 0 will swap. And 10 and 6 will swap. And so that's what our set of numbers looks like after one pass. And our 10 has gone down to the bottom. All right, so now we do a second pass, and we do exactly the same thing. Compare the 2 and the 5, those are in the right order. Compare 5 and 3, those are out of order, so swap. Compare 5 and 1, those are in the wrong order, so swap. 5 and 8 are fine. 8 and 7 are in the wrong order, so swap. 8 and 0 are in the wrong order, so swap. And 8 and 6 are in the wrong order. And 8 and 10 are fine. And I'll blow through one more really quickly. So 3 and 1 will get swapped. 5 is fine, 7 is fine, 7 and 0 will swap. 7 and 6 will swap. 8's fine, 10's fine. Okay, so our original set of data was unsorted. After one pass, we know this number on the bottom is the biggest. After two passes, we know these two numbers are the two biggest. After 3 passes, we know these 3 numbers are the biggest. If we have n numbers to sort, we know that after n passes, all of our numbers are going to be in the correct position. Make sense so far? Okay, so let's write some code. So let's sort n pieces of data from some array called data. So let's do n passes. You really only need n minus 1, and in fact you may need fewer than that. But first order, let's just do n passes, because we know that we'll have n things sorted, and that's the whole list. So for pass equals 1 to n, and what we want to do in each pass is compare each number to the number after it. Now, if we have a total of n pieces of data, we only really need to do this n minus 1 times, right? We need to compare, the last thing we need to compare is this number right before the end to the number at the end. So for num equals, I'm going to index by 1 just because it makes things easier. I won't do that to you. Go from 0 to n minus 2. So compare n minus 2. So compare data num to data num plus 1. So compare each number to the number after it. And normally I would go up to n minus 1, but since I'm going to compare to that thing plus 1, I'm going up to n minus 2. So num equals 0 to n minus 2. And so if they're out of order, then we want to swap them. So after that if statement, I know that elements num and num plus 1 are in the correct order now relative to each other. And then this curly bracket is the end of whatever pass we were just doing. And then this curly bracket is the end of all passes. And that is your whole algorithm. Now you can optimize this. For example, suppose the number that the data that you're trying to sort looks like this. Each time you go through, every number is going to be in the correct position relative to the number after it. You're not going to swap anything. You can go through this 8 times, and when you're done, this is exactly what your array is going to look like. You haven't done any harm by making 8 passes, but you haven't done any work either. Well, you've done work, you haven't done anything productive, right? And if these two happen to be in the wrong order, the first time you go through, you're going to swap these. And the second time you go through your second pass, there's not going to be any changes. And the third pass and fourth pass and so on. So basically, any time that you make a pass, if you don't swap anything, you're done. You can keep making passes, but you won't accomplish anything. So you could throw a flag in here. Whenever you swap, you could set a flag saying, hey, I made a change this time. Keep going. And then down here, if you find out that you've gone through the whole pass and you haven't changed anything, you can return right at that point. Right, so it's like playing solitaire. If you don't take any cards out or move any cards, by the time you get to the end of the deck, you know that nothing's going to change the next time you do this either. So you can make it a little more efficient like that. Also, since after 3 passes, we know that these 3 numbers are in the correct spot, we don't need this inner loop to go all the way up through the last element, right? We only need to sort this smaller set. So we could actually change this index each time that we go through to something like n minus pass plus 1 or something crazy, right? And that'll reduce how much work we have to do. But you know, for bubble sort, I'm too lazy to do any of that, right? I've never done any of those things except when I was doing this in class. If I need a bubble sort, I just do this. I don't think about it. Because computers are fast, they do billions of things a second. Close enough. But if you're trying to sort billions of pieces of data, that's a different story. So you can start making these enhancements, but it turns out that the relative time complexity of a bubble sort doesn't change with any of those things. It might double the speed, but it doesn't really significantly change how horrible bubble sort gets as your numbers get larger and larger. It's exactly n squared, yeah. So the measure of, and this is something we'll drill into in 222 also, but the measure of how ugly an algorithm is time-wise is not how many seconds it takes to run on a certain set of data, because that depends on your CPU, it depends on all kinds of things. The real measure of an algorithm's efficiency is more like if you double the amount of things that you're processing, what happens to your processing time? Does it also double? Does it go up by more than 2? Does it go up by less than 2? Right? And bubble sort has this characteristic that if you double the amount of numbers, you quadruple the amount of time. If you have 10 times as many numbers, it takes 100 times as long. So if I increase my number of data by 1,000,000, right, bubble sort will take 1,000,000,000,000 times longer to run. And in that sense, if I can double the speed of the algorithm, I don't really care, because 1,000,000,000,000 times longer is a deal breaker, right? And it turns out selection sort and insertion sort are exactly the same way. Double the amount of data, quadruple the amount of time. So this is something that we'll call big O. And we'll say that these are order n squared, or big O of n squared, which basically says 10 times as much data, 100 times as much time. So in 222, we'll review these kinds of sorts, but we'll spend a lot of time talking about more efficient sorts, which do much better than order n squared. Things where if you have 1,000,000 times as much data, it takes 6 times as long, which is pretty cool. All right, so how do we do the swap business? How do we swap x and y if they're integers?
You need another variable to hold 1 while you're
Yeah.
doing swap.
I mean, we'd like to do this, set x equal to y and y equal to x, but that doesn't work in a procedural language because when we say y equals x, x has already been set equal to y. So we use a temporary. Right, so set a temporary to x, set x equal to y, and then set y equal to that temporary. Can you do this without a temporary? You can. I won't tell you how, but if you're bored, play around with it. See if you can figure it out. Because there's a way to swap two integers without using a third variable. It's weird though. All right, so one wrinkle on this. When we're doing PA4, we're not sorting a bunch of integers, we're sorting a bunch of strings by their length. Right, so
Just by the number of times they show up.
no. It's sorted by the length of the phrase, regardless of how often they show up. So the shortest phrases come out first and the longest ones come later. So that does not really change a whole lot in our algorithm though. It's really just this swap business and this comparison. So picture your dictionary. I think I change the name of this variable every time. That's a feature. So dictionary is 1,000 phrases, 201 characters for each phrase. So if dictionary num is bigger than dictionary num plus 1 in terms of its length, right? So here you can use string length. Oh, thanks. So dictionary is 1,000 by 201. If string length of dictionary entry num is bigger than string length of dictionary num plus 1, then we want to swap those two strings. So again, we need a temporary variable, but our temporary has got to be a string. So I'm just going to make a character temp that holds 201 characters. And same thing, we'll take the first string, put it in temp, put the second string in the first, put the temp into the second. But we can't just say something like temp equals, because that doesn't copy strings, that copies pointers. Right, so we need to actually copy character by character. And how do you do that in C? Yeah, strcpy. So it's a built-in function. You can prototype it in string.h, and it takes two strings, a destination and a source. And it copies character by character, including the null terminator, from the source to the destination. So that's what you want to use. If you use equals to assign, you're going to get weird results that may look right for a while, but then they'll break eventually. So string copy into temp from, say, dictionary num, and then copy dictionary num from num plus 1. And then use your temp.
Wouldn't you also have to sort all your count integers so they still line up with the right?
Yes. So
Also using structure,
if you're using parallel arrays, then right, good point. So you have to also swap the number of times that you've seen each phrase. If that's in another array, do the same exchange there. So suggestions would be, write yourself a bubble sort. Takes an array of integers, sorts it, prints out the sorted array. Right? Take a break from string processing. Start a new program, new function, call it sort, call it whatever you want. Just feed it an array of integers, tell it how many integers you have, have it do this thing, and call that with an array, right? You can set up your array by hand if you want. You can say integer data bracket 10 equals curly bracket, and you can list your numbers inside there, right, to initialize it. Or you can type them in if you want to be fancy. Pass it to your sort function. When you come back, make a for loop, print out your data, it should be sorted, right? That lets you nail down all the logistics of the sort itself, right? And try that with edge cases, data that's already sorted, data that's completely in the reverse order, things that only have one number in them, and so on and so forth. Get that totally working, and then make yourself the same thing, but something that sorts an array of strings. And this business, right, of swapping, you can throw that into its own function. Because that's fairly hairy code. It's got a temporary variable, it's got some string copies and so on. Make a function that takes two strings and swaps them. And forget about sorting. Just make a swap function, make a main program, type in two strings, call swap, print out the two strings. And exercise that, try some edge cases, try empty strings, and so on and so forth. And once you have a swap function, right, this becomes just a call to swap. Swap dictionary num, comma dictionary num plus 1. Right? So keep looking for opportunities to break your problem down into smaller and smaller pieces. Right? We're really good at tackling small problems usually. Right? Your large problem is to write PA4, right, which I've warned you will take probably a good part of 2 weeks. But writing a function that swaps two strings, it's a few lines of C, right? But if you do that and you test it and you're convinced that that works perfectly well, now writing a bubble sort to sort strings becomes a whole lot easier. Because you don't have to figure this stuff out in the middle of it, you just call your swap function. And once you have a function that sorts an array of strings, your main program gets a whole lot easier, because at the end of your program, when you want to sort your dictionary, you just call sort. And you're done, right? So keep modularizing, keep looking for these opportunities, and try to get in that habit, because it makes things easier as you do this. Does that make sense? All right. Yeah, so if you use structures, you can do something different. And structures make this nice, but I'm not requiring you to be fluent with structures for this. So you can use two arrays, phrases, and counts, or you can make a composite variable that has both.
Makes the whole thing really easy.
Yeah, it does. All right, any other questions on that? Well, let me start doing some review. I posted a study guide on Canvas, but let's start looking at that, and we'll continue it tomorrow. But we'll leave plenty of time to get through it. So possible topics for the midterm. There's really 3 sections to the midterm. One section on basic Linux stuff. That's a smallest piece of the exam. A section on C programming, a section on Bash programming. Those are the biggest pieces. So about equal amounts of C and Bash, and a little bit of some Linux stuff. So let's start talking about the Linux stuff first. Basic Linux commands. These are commands that we've been using up here. These are commands you've probably been using in your daily experiences with Linux, right? So cat to show the contents of a file, echo to display something to standard out, ls-l to look at lists of files, change mod to change the permissions on a file, mainly so you can execute, move to rename a file, cp to copy, rm to remove or delete, wc we keep using as examples for things that show you how many lines there are in standard, and date, which shows you the date, pwd, which shows you your directory, right? All the basic stuff that we keep using. If there's some obscure command that I've mentioned once on the way out the door, I'm probably not going to give you 20 questions on that command, right? Stuff that we've been using, stuff that you should have been encountering is really what I'm after here. Redirection of input and output, right? So here's ls. If I say ls greater than output, instead of showing me the results of ls on standard out, it sends it into this file. And if I look at that file, it's got the output of ls. Right? If I say ls-l greater than output, and I look at output, it's got the result of ls-l. All right, a less than sign lets us redirect standard in. Classic example will be testing PA4. When you run PA4, it expects you to type in a bunch of text, and then it's going to generate a list of phrases, right? If you don't want to keep typing in a bunch of text, make yourself a test file and just say PA4 less than whatever that file name is. And classic test file is going to be warandpeace.txt, right? Not classic, but that's kind of the final test to make sure your code doesn't blow up. But make yourself a test file. There's a sample in the ODP. Throw it into a file and use less than to redirect.
So for the less than, you command first,
Mhm.
and then less than in the file name.
Correct. PA4 less than, let's see if I have a test file. Right, so command less than file name. So it reads from that file instead of standard in. All right, pipe is similar, but it actually takes the output of one command and sends that to the input of another command. So we can say command 1, pipe command 2, and standard out of the first command feeds into standard in of the second. So example of that, if I say ls-l, that shows me a list of files in my directory. If I say word count, that reads how many lines, characters, and words I have in standard in. So if I say ls-l and I pipe that into word count, it takes the output of ls-l and uses that as the input to word count. So it tells me ls-l produced 11 lines, 92 words, 541 characters. So it's a way to combine commands and take the output of one, feed it into something else. And I could also have done this, ls-l greater than temp, and then word count less than temp, and I get exactly something different. That's weird.
It is.
Oh, because now I have a file called temp. But it's the same effect, right? But with a pipe, we're not actually creating these temporary files.
So greater than says to put the output into that file.
Mm-hmm. That put the output into temp. So temp looked like that. And then I said take word count, but feed that input from temp. And that's the same as just doing ls-l.
Greater than does.
Greater than sends standard out into a file. Less than reads standard in from a file. And then a pipe connects standard out of the first command to standard in of the second command. All right, so quotation marks. If you use double quotes, it basically turns what's inside here into a literal. So if I say double quote 2 plus 3, that's just 2 plus sign 3, right? But if you have a $sign in there followed by a variable name, it'll be replaced with the value of that variable. So x equals hello, y equals x is $x. If I look at the value of y, it says x is hello. Right, so $x gets replaced by the value of x. But if I do this inside single quotes are purely literal. So now if I look at the value of y, it says x is $x. Okay, that's the big difference between double quotes and single quotes. So single quote. says don't expand $sign variable. Back quotes are a different creature altogether. If you have a command inside back quotes, it basically says run that command, capture standard out, and then replace this expression with whatever standard out was. So if I say x equals back quote date, that runs the command date, takes the output of it, right? So date generates a thing like that, and this basically said x equals whatever date produced. So now if I echo $x, it was whatever the value was that date produced when I ran that command. So if I say echo quote, the date is back quote date, which is fun, right? This back quote date says, okay, stop everything, execute the date command, capture standard out, and then pop the result of that standard out in place of back quote date. So this says the date is blah, 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 which is fun. So if I say echo your directory is back quote pwd back quote period, right? It says your directory is, there's my directory with a period at the end. But if I do this in single quotes, it says your directory is back quote pwd back quote period, right? So single quotes pretty much make it literal. Double quotes replace $signs with values of variables, and they replace back quotes with standard out from running the command inside the back quotes. Good? All right, so we'll pick up from there. We'll talk about file systems and all this other stuff, but this is posted on Canvas if you want to take a look at it. So we'll pick up from there tomorrow.